My name is Yuki Tani, SEM Applications Engineer at Hitachi High-Tech America. Today, I will introduce our Schottky FE-SEM series, SU3800SE and SU3900SE. So first, I will give a brief overview of the product, and then I will explain the imaging capabilities, including some unique detector feature. And then finally, I will show our automation tool that support efficient and repeatable SEM workflows. So let me start with a quick overview. We have developed the SU38 and 3900 SE to meet wide variety of the analytical requirements. We developed the new Schottky optics, which provide improved resolution compared to previous model, SU5000. And for this product line, we have standard chamber model, SU3800, and large chamber model, SU3900SE. Also, we have multiple imaging detectors to support various applications. Our unique STEM detector is available for the bright field transmission imaging. So I will show you some application data using this holder data. And lastly, automation capabilities. In this talk, I will introduce recipe creator tools to automate analysis workflow. And I also introduce some new image processing tools. So let me explain each feature in more detail. So first, let me talk about hardware design. Our new hardware offers higher resolution even at low accelerating voltage. Compared to previous model, the resolution has improved from 3 to 2.5 nanometer at 1 kb and from 2 to 1.6 nanometer with beam deceleration mode. This is very useful when observing a beam-sensitive sample or top surface structure like zeolite particle. And the system also provides high probe current to support various analytical techniques like EDS analysis, EBSD analysis, particle analysis as well. For the SU3900SE, large chamber models allows the users to handle heavy and large samples. So as you can see here, it can accommodate samples with the diameter of 300 mm and height of 130 mm. The 5-axis stage can drive samples with up to 5 kg as well. So next, let me explain about the imaging capabilities. So as I said, our system supports multiple imaging detectors to meet various observation requirements. So 4 imaging are available in total. We have SE detector for surface topography imaging. We also have insertable backscatter detector for the compositional information and crystal contrast. For further imaging capability, the system can support additional top detector and ultra variable pressure detector. The top detector can be used for visualizing top surface structure in beam deceleration mode. And UVD detector, ultra variable pressure detector for the SE imaging under variable pressure mode. And UVD detector can switch between topography mode and shear mode. I will explain this in more detail later. And of course, it can mix 2 signals and capture 2 images simultaneously. So today I will explain more details about the UVD detector. So UVD allows SE imaging of non-conductive sample under variable pressure mode. In this mode, gas molecules are introduced into the chamber, and these molecules generate positive ion, which help neutralize surface charge. This means we can observe the non-conductive sample without metal coating. So on the right, you can see the image comparison. SE image in high vacuum mode shows strong charging, but UVD image gives a clear surface structure. In addition to topographic imaging, the UVD can be used for the cathode luminescence shear imaging detector. By turning off the bias voltage to the detector, the detector switches to the panchromatic shear mode. So this mode allows detection of the light emitted from the sample surface which is valuable for studying luminescent materials. On the right shows, you can see two images from the same sample. One shows topographic imaging, and other one shows CL information from the material. And the UVD detector can also be used for the transmitted electron imaging by using UVD stem holder. This holder accepts standard TM grids. It works in both high vacuum mode and variable pressure mode, and no additional modification and hardware items are required. So it's very flexible and easy to use. This is a UVD stem holder. With this holder, electrons pass through the sample and hit the scintillator. Then light signal generated from that interaction is detected by the UVD detector. This is the principle of the UVD stem imaging. So here is an example of the high magnification imaging using stem holder. Sample is fuel cell. We captured images at 200,000 magnification and 500,000 magnification. As you can see, we can clearly observe the fine structure of the nanoparticles even at this magnification range. So this shows that UVD stem system is suitable for the nanoscale analysis. So far, I've talked about the hardware design and imaging capability of the systems. Let me move on to the automation feature. This is main topic of my talk today. So our system includes powerful automation tools called EM Flow Creator. This software allows the users to create a recipe by simply drag and drop SEM commands like accelerating voltage setting, magnification, stage movements into flowcharts. So this means no programming skills are required. So it also supports CSV file input-output for easier stage movement control, and also for advanced users, Python-based script can be utilized to design custom UI for your workflow. To automate imaging, accurate target detection technology is very important. So EM Flow Creator includes several image processing tools to support automated target detection. One useful method is template matching. When it finds a matching structure like this, system can automatically move the stage to center that feature like this. This function is useful when you need to locate repeated structure in your sample. Another method is binarization and target extraction. So this is a new feature. Black and white image is generated, and then the system selects the target particle based on the size and shape. So both methods are built into the block-based recipe system, so no programming is required. It's good. And so, let me explain about the template matching first. Here is an example of the automated workflow using template matching. The sample is wire bonding structure. We use template matching to detect bonding pattern. Once matching structure is found, system automatically moves the stage to the bonding area, and then for each location we captured at 4 magnification, 1000, 2.5,000, 5,000, and 10,000. Let me show you a workflow using a video. On the right, you can see a user interface of the EM Flow Creator. The flowchart shows each step in automated workflow. On the left side, you can see the live imaging. Let me start the video. This will capture images at 14 locations automatically. So first, capture the image at 1000 magnification and execute template matching, adjusting the stage position, and then increase the magnification and capture the image, execute template matching again, adjusting the stage position, and then capture again, and finally zoom into 10,000 and then capture the image. After capturing the image, the stage moves to the second location and repeat the same process. So it observed 14 locations automatically. So next, let me show you an example using a finalization and target extraction. The goal of this workflow is to detect and capture images of round-shaped particles that are about 2 micron. So first, SEM captures the low magnification image, in this case 1000 magnification, and then software applies the finalization to highlight features in black and white. As a next step, target particles are filtered based on the specific criteria, in this case, size and aspect ratio. 3 particles are detected. Once target particles are found, stage moves to the detected particle and then captures a high magnification image. After capturing the image, stage moves to the next target, for example, particle number 1, number 2, number 3, and then move to the next area, next location. So let me show you the video to demonstrate automated workflow. So first, execute the recipe. And then move to the starting location. Execute autofocus to get clear image. Then capture the image. After capturing, finalization and target extraction are performed. In this case, 3 particles are detected. And then move to the particle number 1, increase the magnification, execute autofocus, and then capture the image. After capturing, stage move to the particle number 2, then repeat the same process. So after all 3 particles are captured, the stage move to the second location and repeat the same process. As you can see, so the entire process is done automatically. So there is no need to be in front of the SEM. So this is a good advantage of the automation tool. In addition to automated imaging, the system performs real-time measurement of the detected particles. So this includes particle size, area, aspect ratio, and other measurements. And the software also records stage coordinate for detected particle, as you can see here. So these results can be saved and exported or used to guide further analysis. So today I talked about new hardware design, the imaging options, and automation features of these systems. So this system can offer improved resolution compared to previous model and more imaging flexibility with multiple detectors and stem holder and easy operation with the automation workflow. So these features support efficient and consistent SEM analysis for both beginners and experienced users as well. This is the end of my presentation. So thank you very much for your attention.